Hello everyone and welcome back. This is going to be our last lesson in Chapter 2, and I want to remind you of what we called a piecewise definition in the last lesson when we were talking about absolute value functions. We said that y equals, and we then had a brace, and then we had x when x is greater than or equal to 0, and we had the opposite of x when x is less than 0, and that was the absolute value defined as a piecewise function. So today what we're going to do is talk more about piecewise functions. And then we're also going to review the topic of graphing linear inequalities. So we have two parts to our lesson today, and this is notes number 8. Piecewise functions and graphing linear inequalities. So let's take a look at number 1. We have a piecewise function, g of x, and it equals x minus 3 if x is greater than 3, and it equals x plus 2 if x is less than or equal to 3. So I want you to think about the line y equals x minus 3, that's the top piece, and I want you to think about the line y equals x plus 2, that's the bottom piece. So I'm sure separately you could graph either of those two lines. We know the slope, we know the y-intercept. So we're going to have a piece of one line and a piece of another line. And the place where one piece ends and the other piece begins is at x equals 3. So what I'm going to do is plug in 2 points into the top piece, because we know if we're drawing a line, 2 points is enough. And then I'm going to plug in 2 points into the bottom piece, and then we can draw that line as well. So for the top piece, I always use the number where we're breaking from one piece to the other. So use 3, substitute it in, 3 minus 3 is 0. The thing is, we're going to need to make that an open circle because we're not actually including 3, it has to be greater than 3. Now for a second point, choose any number you want that's greater than 3, so I'm going to choose 4. Plug it in, 4 minus 3 is 1. So we have an open circle at 3, 0. I'm going to go ahead and label my axes, showing the scale. Always show your scale, even if it's ones. So 3, 0 is the starting point, and then we go through 4, 1. Start at 3, 0, go through 4, 1, and keep going. And we have that piece. Okay, for the other piece, again, I'm going to use 3 because that's the end point of the piece. So if I substitute 3 in, I have 3 plus 2, which is 5. And that's going to be a closed circle because we're using less than or equal to, so we're including the end point. And then for a second point, choose any number you want that's less than 3. So I'm going to choose 2. Plug it in, 2 plus 2 is 4. So start at the end point, which is 3, 5. Plot that point. Go through the other point, 2, 4. And keep going. So starting at the end point, through the other point, and keep going. Okay, when you look at your graph, it should look like a function, so it passes the vertical line test. Anywhere you draw a vertical line, it only goes through one point. Even right here, it's only going through one point because the closed circle is a point and the open circle is not a point. Okay, so that's the graph. And then for part B, we're going to evaluate g at a couple of different values. G of negative 2. So which piece would you plug negative 2 into? Does negative 2 fall into the x is greater than 3 category, or does it fall into the x is less than or equal to 3 category? I would say that negative 2 is less than or equal to 3, so we're going to plug negative 2 into the bottom piece. So we have negative 2 plus 2, which is 0. So according to that, hopefully our graph goes through the point negative 2, 0. And it does. We can see that point on the graph. We're also going to evaluate g of 5. So where do we plug in the 5? Which piece does it fit into? 5 is greater than 3, so we're going to plug it into the top piece. So we have 5 minus 3, which is 2. So that tells us that on our graph we should have the point 5, 2. And we do. Okay, so that's how you draw a piecewise function. Here's another example, and this time we have 3 pieces. So let's imagine what those pieces look like. The top piece is the line y equals x. It's a part of the line. It's a piece of the line. So we know what that would look like by itself. The middle piece is a part of the line y equals x plus 1. And the bottom piece is a part of the line y equals negative 1. Now if you have y equals a constant, you know that's going to be a horizontal line. So we're going to have a piece of one line, a piece of another line, and a piece of another line. So let's go ahead and find some points on each piece. So just like in problem number 1, I always use the endpoint that's given. So for the top piece, I'm going to use negative 1, plug it in, and we just get negative 1 because all we're plugging it into is x. And that's going to be an open circle since we just have a less than sign and not less than or equal to. Now we need a second point. So we can pick any number we want that's less than negative 1. So I'm going to choose negative 2, plug it in, and I get negative 2. Okay, so let's go by ones again on this graph and start by plotting the open circle at negative 1, negative 1. And then we also have a point at negative 2, negative 2. So starting at the open circle, go through the other point and keep going. Okay, let's do the middle piece. It has two endpoints, so those are going to be the two numbers we use. So negative 1, plug it in, negative 1 plus 1 is 0. That's one endpoint, and it's going to be a closed circle. And then the other endpoint is 2. Plug it in, 2 plus 1 is 3, and that's also going to be a closed circle. So we have negative 1, 0, closed circle, 2, 3, closed circle, and then the line segment in between, and that's the middle piece. Does it look like the line y equals x plus 1? Does it look like it has a slope of 1 and a y-intercept of 1? I hope so. Okay, now for the bottom piece. Because the endpoint is 2, I'm going to use a 2, plug it in, but when you plug it in, your output is always negative 1. It's a constant output. So just 2, negative 1, and that's going to be an open circle because we just have a greater than and not a greater than or equal to. And then we can choose any other number we want that's greater than 2, so I'm going to choose 3, plug it in, and I get negative 1. So we have an open circle at 2, negative 1. And then go through the other point, 3, negative 1, and keep going. Okay. Now, I don't think we have an example of this, but there could be times for other graphs where you draw a piece and it has an open circle. And then when you go to draw the other piece, you have a closed circle that lies right on top of your open circle. If that's the case, the closed circle just fills in the open circle. So you can be on the lookout for that. For the third example, we're going to do it in reverse. So I've given you a graph, and your goal is to write the piecewise definition. So what that means is you write the part that says f of x equals, and then we have our brace, and then we're going to have 3 pieces. So look at the first piece on the left. It's just a horizontal line, so it's a constant, and it looks like it's at a height of 2. So it's the line y equals 2. Then look at the next piece, the middle piece. It's another horizontal line, and it's at a height of 1, so that piece is the piece y equals 1. And then let's take a look at the third piece, and it's part of a line, and we know it goes through the point 2, negative 1. And we can tell pretty clearly that it has a slope of negative 1. So we can find the equation of that line. So I'm going to use point slope form. Y minus y1 equals m times x minus x1. Substitute negative 1 in for y1 because of the point 2, negative 1. Substitute negative 1 in for the slope, and substitute 2 in for x1. So we have y plus 1 equals the opposite of x plus 2. So we have y equals the opposite of x plus 1. Okay, so that is that piece. So all we need to do when we write the definition is write the part that goes after the equal sign, because we already have the f of x equals part, and that's our y equals part. So f of x equals 2, f of x equals 1, and f of x equals the opposite of x plus 1. Okay, Sometimes you see a comma, sometimes just a space, sometimes you see the word if, sometimes not. It doesn't really matter. So now is where we write the domain for each piece. So when you look at the line y equals 2, notice it's going from x equals -2 to x equals 0. And it includes -2 and it does not include 0. So -2 is less than or equal to x is less than 0. And then look at the middle piece. Notice it goes from x equals 0 to x equals 2. It includes the 0 and it doesn't include the 2. And then the third piece, it starts at x equals 2 and it keeps going and it has a closed circle. So x is greater than or equal to 2. So that's how we would write our own piecewise definition. Okay, the next part, I think I'll just continue and do this all in one video because it's not going to take very long for us to do part 2. This is something that I suspect you did in Algebra 1, but even if you didn't, I think you'll pick up on the extra parts pretty quickly. So we're graphing x is less than or equal to 5, but I'm not referring to a number line graph, I'm referring to a coordinate system graph. So we're using x and y right now. If you have x is less than or equal to 5, start by just thinking about the line x equals 5. So that's going to be a vertical line, 5 units to the right of the origin. So we'll draw that line. Now we also want any x value that is less than 5, so less than or equal to 5. So everything to the left will have an x value less than 5, so we shade. So that's how you draw that kind of graph. You have a solid line if it says equals to, you have a dotted line if it doesn't say equals to, and then you shade. So let's take a look at number 5. It says greater than, it doesn't say greater than or equal to, so it's going to be a dotted line. Dotted line means don't include those points on the line. Now I'm going to focus on the line 3x minus 4y equals 12, and it's in standard form, and my favorite way to graph in standard form is to find the intercepts. So if x is 0, what would y have to be? -3. And if y was 0, what would x have to be? 4. So I'm going to plot the point 0, -3. And plot the point 4, 0. Let's draw the line and remember it's going to be dotted. And then we have to figure out whether we're shading above the line or below the line. You can't always trust the direction of the inequality. If your equation is not in slope-intercept form, then don't trust the direction of the inequality. So what we can do is we can use a test point. And my favorite test point is 0, 0. So if 0, 0 is not on your line, then use it as a test point, substitute it into the inequality, and see if it makes it true. 3 times x minus 4 times y is greater than 12. So that would be 0 minus 0. That would be 0 is greater than 12, and that is false. So that means don't shade 0, 0. It's not a solution. So don't shade the region that includes 0, 0, and that tells us we're going to shade below. So every point in the shaded region is a solution. The points on the line are not solutions. That's why we made it a dotted line. Okay, I think this is the last one. We're going to do a word problem. You have 2 part-time summer jobs, one that pays $9 an hour and another that pays $12 an hour. You would like to earn at least $240 a week. Write an inequality describing the possible amounts of time you can schedule at both jobs. Graph the inequality and then identify 3 possible solutions. So let's say that you work X hours at the $9 an hour job, and let's say you work Y hours at the $12 an hour job. Now, there of course would be some restrictions on how many hours you can work altogether and how many hours are in a week and all that kind of thing. But just kind of setting that aside for the moment, the amount of money you make at the first job would be 9x, the pay per hour times the number of hours. And the amount of money you make at the second job would be 12y, $12 an hour times the number of hours. And you're hoping to earn at least 240, so that would be greater than or equal to 240. So there's our inequality. Okay, so we've written the inequality, and then we're going to graph it. And we can divide this by 3. We can divide both sides of the inequality by 3. That will make the numbers a little easier to work with. And then if we want to find intercepts like we did on the last problem, if x is 0, then y would have to be 20. And if y is 0, then x would have to be 80 thirds. And 80 thirds, I love improper fractions so much more than mixed numbers, but for graphing, we need to know that the mixed number is 26 2/3. So, it's going to be a solid line because of the equal to, and we're going to have a point 0, 20, and a point 26 2/3, 0. We can draw that line, and notice I'm only using the first quadrant because you couldn't have a negative number of hours at a job, so both of the numbers of hours have to be either 0 or positive. And then to finish the problem, the last thing we need to do is identify oops, I didn't finish the graph, did I? I have to shade. Which way am I going to shade? What happens if I test 0, 0? 0 plus 0 greater than or equal to 80. Nope, that's false. Of course, you can't work 0 hours and make any money, so we're going to shade above. Okay, now for the 3 possible solutions. You have infinitely many options. You can choose a point that lies on the line, or you can choose a point that lies in the shaded region. So many possible answers. I would say an easy one is just 0, 20, 0 hours at one job, 20 hours at the other job. And then maybe you just pick something that's nice and easy to find out here in the shaded region, like 10, 25. Of course, if you go too far out there, you're going to get into answers that are not reasonable for the number of hours in a week. Let's just do one more. How about 25, 5? Okay. Oh, there is one more problem. I just keep surprising myself with more and more parts of this lesson. That's pretty exciting. This is the last one. What I thought would be fun to do is to combine ideas here. We have an inequality. We also have an absolute value graph that has been transformed. So I have multiple graphs because, as you know, I like to do my transformations step by step. And in terms of the inequality, we're going to have some shading, but I'm not going to worry about the shading until I get to the very end of the problem. So the first thing to do is just remind ourselves what y equals the absolute value of x looks like. We have that V-shaped graph. And then how about y equals the absolute value of x plus 2? So we're going to shift the whole graph which way? That's right, left 2. Good, you got it. Okay. And then I think I'll make that go a little bit straighter. Trying to get the slopes correct on that. Okay, that's better. And then how about y equals the opposite of the absolute value of x plus 2? What's that negative going to do to it? Very good. It's going to reflect it across the x-axis. Okay, and then let's subtract the 1. And at this point, I'm going to go ahead and do my shading once I have the shape in place. So what does subtracting the 1 do to it? I know you know. You're right. Shifts it all down 1. You know your transformations. That's good. It is solid because of the equal to. Now let's test 0, 0. 0 is less than or equal to the opposite of the absolute value of 0 plus 2 minus 1. Let's see if that's true or not. 0 is less than or equal to negative 2 minus 1. 0 is less than or equal to negative 3. Nope, that's false. So we're not going to shade 0, 0. So in this case, our options are to shade outside the V or inside the V. Since we're not shading 0, 0, we're going to shade inside the V. Okay. So here we have today's assignment. We have a little bit of piecewise functions and we have a little bit of graphing inequalities. Thanks, everyone.